Hi folks, we're back to talk about gravity. If you missed class this week, or if you're feeling uncomfortable with the lab or the math or just want to stay and hang out, you're welcome to join me after class next week to do the lab, the rotational motion lab. Um, the worksheet I've somehow deleted from my hard drive. I'm going to have to retype. So I'll bring hard copies of the worksheet next week. But this is a lab where we have a little mass that rotates at a certain radius. I don't know if you can see a little blue mark on the string right there near the mouth of the pen. If I move it this way, maybe you can. At that radius, which is 6 inches, which I think is a little short. I think I'm going to change that for next year. And we can change the amount of centripetal force to either 2 or 4 washers by adding or subtracting washers there. And in my video from last week, you kind of saw the gist of the lab. So hopefully you'll join me for that if you missed class right after class this week. Or you can make other arrangements, or I can just give you the sheet and you can try to do the lab at home. It's a little confusing, so if you want to join me, that would probably be the easiest way to get it done. So let's talk a little bit about this theory of gravity and how the planets orbit and how you do the math associated with this module. So why doesn't gravity with the sun and the Earth and the other planets act just like gravity here on Earth? I mean, if I drop this pen, it just falls straight down toward the center of the Earth because of the force of gravity between the Earth and the pen. It doesn't start to orbit the Earth. Why then can we say that gravity is the reason that Earth orbits the sun instead of falling straight toward the sun and being destroyed? Well, the reason is because this pen doesn't have a huge velocity in a direction perpendicular to straight toward the center of the Earth. Okay, so if you think about the word perpendicular, right, that means at a 90-degree angle, right, perpendicular. This pen has a velocity of 0 perpendicular to the Earth, so it falls straight down. What happens when the Earth and the other planets are orbiting? They have a huge velocity vector that's pointed perpendicular to the sun. Okay, so instead of the sun's gravity pulling the Earth straight into the sun, what happens is the sun's gravity pulls the Earth in, but that velocity vector causes the Earth to fall and miss, fall and miss, fall and miss, just like satellites orbit Earth. Earth orbits the sun. So the centripetal force causing Earth to orbit, F sub c is how I abbreviate centripetal force, is caused by gravity. So the sun is pulling the Earth toward it, but Earth's perpendicular velocity causes it to fall and miss, essentially creating a nearly circular orbit, an ellipse, and the other planets as well. So that is why the Earth doesn't just fall straight in to the sun like this pen falls straight down toward the center of the Earth. Gravity provides a centripetal force with a velocity vector that's perpendicular to, oh dear, that's not visible. Let's come and take that over. I hope the last video wasn't cut off like that. Anyhow, so what causes gravity? Well, we don't actually have one theory that has completely won out over the others. We still kind of have two theories. My preferred theory is Einstein's theory of general relativity, which says that gravity is not a force at all. And he demonstrates that with something like this. So here's a mass, and mass bends space. Mass bends space just like if you're sitting on a couch and a large person or dog or something sits down next to you, and it bends its couch cushions in, and you kind of fall toward the large object. Gravity is caused by something like that, that mass bends space, so anything that was traveling in a straight line is just bent in toward that large mass. If you watch the video again of the huge frame, circular frame with the big spandex thing and a mass in the center, you can kind of see how you would apply the theory of general relativity to that. because mass is just bending space. So it's not actually a force, it's just an effect of mass bending space. The other theory that Dr. Weil puts forth is the graviton theory. And because in the next module you'll learn about electromagnetism and the equations that govern the electromagnetic force, or the electroweak force if you combine them, and you see a perfect symmetry between those equations and the equations that we can use to calculate gravity. So if there's a symmetry, the hypothesis is that there must be also a similar cause. The force of electromagnetism we know is caused by particle exchange, photon exchange. So the hypothesis is that gravity is also caused by particle exchange. I don't see how that's even remotely possible. The science can be surprising. So the graviton theory. Particles are exchanged between objects with mass, and so they have an attractive force between them. In this case, gravity would actually be a force, and I just don't see how like the sun and earth are exchanging particles at such a fast speed that the force of gravity exists. Like I don't understand how that's possible. But like I said, science is surprising, so he puts that out there as a possibility. And there is perfect symmetry between the equations that govern this force and gravity, so I don't know. But I wanted to go over the Module 11 quest, which is in the Dropbox, just to make sure you're feeling comfortable with the math. Last week's videos had some of the on your own and the study guide problems. So hopefully, if we go over the Module 11 quest, you'll feel comfortable with this math for the test. And because it's essentially identical to the math in the next chapter for electromagnetism, it's really good to master this now, because you'll be seeing it over and over for the rest of the year, basically. So these first two questions are very similar to the test, as it tells you at the top of the Module 11 quest. And the first one says, oh, I want to talk about gravity a little bit before I do problems. So, and the equation. So the equation that we use for gravity, the force of gravity is directly proportional to the masses. If you increase mass, the force of gravity increases, which should make sense. And the distance or radius squared, force is inversely proportional to the distance between the two objects squared. So if you increase distance, you decrease force, because when things are further apart, the gravitational force between them is smaller. When things gain mass, gravitational force increases. So that's our equation, and now we'll look at the first problem on the quest. The gravitational force between two objects, mass 1 is 4 kilograms, so I'm just going to mark mass 1 equals 4 kilograms, and then we'll just worry about how that changes. Mass 2 is 10 kilograms. Is measured when the objects are 1 kilometer apart. So we'll put distance as 1 kilometer, and I'll make that look like a 1. Okay, so that's how the problem starts. And in physics, you would learn that there's a constant that you multiply by. You would learn how to actually calculate the gravitational force from this. But for you guys, all you're worried about is how much the masses and the distance change and how gravity changes from one situation to another. So you only care about the factor of change, not the original numbers or the end numbers. So if the 4 kilogram mass is replaced with a 16 kilogram mass, so all you have to worry about is you multiply by what to get the new figure. What's the factor of change? The factor that you need to multiply by to go from this to that. So 4 times what is 16? Well, 4 times 4 is 16. So my factor of change is 4 for the first mass. The problem says the second mass, the 10 kilogram mass, is replaced with a 60 kilogram mass. So then I want to know what factor of change it experienced. So 10 times what is 60? Well, 10 times 6 is 60. So its factor of change is 6. And in the first problem, the distance doesn't change at all. So I don't need to worry about that. So then I just plug into my equation Okay, simply plug in the factors of change. So the force equals the factor of change for the masses, which is 4 times 6, and the distance doesn't change, so I don't worry about that. So the force changes by this many times, 4 times 6, which is 24 times. And since 24 is not a fraction, it's in the numerator, it is increasing. So the force of gravity increases by 24 times. I think, yep, in the next problem we'll see what you're going to come up with if the gravitational force is decreasing. But in this problem, it's increasing. It'll be 24 times stronger gravity when these masses increase. Okay, so that's request problem 1. Oh, I just left the equation. Okay. Well, it can't hurt to write the equation again because you need to memorize it. So force is, there's really a constant, and then the change in mass 1, the change in mass 2, and you divide by the change in the distance and you square that number. So the second problem says the gravitational force between two objects is measured when they're 5 centimeters apart. The masses don't change, but the distance between them is increased to 15 centimeters. So distance starts out at 5 centimeters, and then you have to multiply it by that factor of change and get 15 centimeters. Okay, so 5 times what is 15? Well, 5 times 3 is 15. So 3 is my factor of change for distance, 15. So move that. Okay, so then I just plug that in. I say, well, my masses don't change. When you multiply something by 1, it doesn't change it, so I'll put a 1 there. And then I plug in my factor of change here for distance, right? So it changes by 3. And then I square the change in distance because the equation has that squared. So then I get the answer here to be 1 over 3 times 3. 3 squared is just 3 times 3, right? And 3 times 3 is 9. So I find the force changes by 1/9. And what that means is force of gravity decreases by 9 times. Okay? The 1/9, the fact that 9 is in the denominator, tells us that force is decreasing by 9 times. Okay, when it's in the numerator, force is increasing. When you get an answer in the denominator, force is decreasing. So, and then if you think that through, it makes sense, because if you have these two objects, and they're at 5 centimeters apart, ooh, I can't get the spatial thing, and then you increase the distance between them, gravity decreases. That makes sense. You want to think through your answers to make sure that you see that they make sense. So when you increase the distance between them, the gravitational force decreases, in this case by 9 times. So if you can keep track of those two problems, you'll be prepared for the test. And then the third one is just a little more of a challenge. It says the gravitational force between two objects, the first one has a mass of 9 grams, and the second one has a mass of 7 grams, is measured when they're 2 centimeters apart. Okay. Mass 1 is decreased to 3 grams. So what can I multiply 9 by to get 3? Okay. 9 times what is 3? Well, obviously I have to multiply by a fraction to make the number get smaller. So 9 times 1/3, or essentially 9 divided by 3, is 3. So my factor of change for that mass is 1/3, right? It shrinks. The second mass, oh, I dropped my paper. Okay, the second mass is increased to 21 grams. So 7 times the factor of change gets us to 21 grams. 7 times what is 21? Well, 7 times 3. So my factor of change for mass 2 is going to be 3 times, because 7 times 3 is 21. It changes by 3 times. It increases by 3 times, that mass. And then the distance, let's see, it's way down here. The distance goes to 1 centimeter. Okay, so 2 times what gives you 1? Well, when it's shrinking, you have to multiply again by a fraction, just like this first mass. right? So 2 times what is going to be 1? Well, 2 times 1/2 is 1, right? 2 times 1/2 equals 2 over 2, which is 1. So the factor of change for that distance is going to be 1/2. Now, here's where we test your fraction skills. We're going to plug into the equation. So up here, force is the factors of change. For mass, 1/3 times 3, right, because the masses are 1/3 times 3. And then the factor of change for the distance, which is 1/2 squared. So now we just do our math with our fractions. 1/3 times 3, well, that's easy. That's 1. And then 1/2 squared. Well, that means 1/2 times 1/2. Well, 1/2 times 1/2 is 1/4. So now you have this answer, but what does that really mean? 1 divided by 1/4. Well, you have a couple options. I mean, you guys know you could do that on your calculator, right? So you could say, what is 1/4? Well, I hope you all know 1/4, or 1 divided by 4, is 0.25, right? You all know that. 1/4 is 0.25, like 1/4 is worth 25 cents, right? A quarter. So then you could say, well, what's 1 divided by a quarter? 1 divided by 0.25 is 4. So if you really need the calculator help, you can do it. But hopefully you guys know how to work with fractions well enough not to need that. So I could just say this. 1 divided by 1/4, right? That's what this means. 1 divided by 1/4 equals what? You know, when you're dividing by a fraction, what you're really doing is multiplying by the reciprocal of the fraction. So the reciprocal of 1/4 is 4 over 1, right? You just flip it over to get the reciprocal. So that means 1 times 4 over 1, right? 1 divided by 1/4 is the same as 1 times the reciprocal of 1/4, 4 over 1. And 1 times 4 over 1 is just 1 times 4. That's 4, right? Okay. So your final answer here is 4. And because it's a number that's in the numerator, right, it's not in the denominator, it's a whole number, so that means that the gravitational force increases by 4 times. So there's a review of how to do the math. Hopefully that helps you kind of have a process, and it's really good to know because it'll appear in the next module and probably the next one also. So hope that you're prepared. Call me if you have any questions, and have a great week.